Great ideas in computer science and math and algorithms, they often get invented and reinvented again and again throughout history. And for many of these great ideas, it's not even clear who was first. Who was the first to invent this idea or that idea? And I thought in this video, I might tell you about one of these great ideas. It's called the greedy permutation, although it goes by other names because, of course, everyone who names it or invents it gets to rename it. I promise, if you have anything to do with data analysis at any point, sometime this approach, this idea will become important to you. And I'm also going to talk about how this greedy permutation idea fits into my research, and sort of in different ways has been woven into the research projects I've been working on for many years. And before I do that, I guess let me properly introduce myself. My name is Don Sheehy. I joined the faculty here at NCSU back in 2019 as an associate professor. And prior to that, I was a professor at the University of Connecticut. I specialize in the design and analysis of algorithms and data structures for mostly problems in computational geometry and topology. So to start with this greedy permutation question, we start with a question. And the question is, what makes a good sample? Let's say I have 1 billion points in the plane. So it's not a high dimensional set, but I just have a lot of points. I'm not going to draw 1 billion dots right now, but pretend that I did. So I have 1 billion points. Now, I also have a certain kind of analysis I want to do on these points. And I won't tell you what it is, but let me just say that the best known algorithm runs in time that is approximately cubic in the number of points. So if you have an order n cubed time algorithm to work with the data set, you cannot work on 1 billion points. I'm sorry. It's 1 billion points. It's just a non-starter for a cubic time algorithm. And if there's nothing I can do to speed up the algorithm, my only hope is to reduce the amount of data. So I might take a subset of this data and try to work with that instead. Now, the question of what makes a good sample then is something close to what would be a good set of points so that my answer on the sample would be close to or give me a good approximation to the answer on the entire data set if I had everything, which is familiar to anyone who studied statistics, and that's why a lot of statistical machine learning problems have this flavor. In this case, my concerns are not so much statistical, but rather geometric. And here's what I mean. In this case, what I would like is a sample, a subset of points that roughly characterizes the shape of this data set. So if there is some opening here, let's say there's kind of a hole with no data here, or there's some kind of hole here, I would like my sample to roughly surround that hole in the same way. And right now I'm starting with fuzzy notions, but I'm going to make this concrete in just a second. What I'd like in my good sample is somehow to capture the geometry of the original set with far fewer points. All right, so what could capturing the geometry mean? I think it often gets characterized in terms of two different properties. One we might call packing, and the other we might call covering. So the packing condition says that there's some minimum distance between my sample points. Let's call it epsilon. So this distance between two samples is bigger than, or at least epsilon. That's my packing condition. So let's again say these red points are the ones that I actually chose in my sample, and the blue points were all the points. So I'm not going to take any 2 points that are too close together. The other property I'm interested in is a covering property. That is, if I take a sample of points and I look, let's say again, at some radius epsilon. These are circles of radius epsilon, and they don't contain any other points as long as I've got my packing condition, but these should cover all the input points. So all the other input points have to be inside or on these circles. And that would be an epsilon covering. So I have an epsilon packing and an epsilon covering. If you have both, that would be an epsilon net. Okay, and so this is a nice notion of what it could mean to be a good sample, is to have an epsilon net for some good epsilon. Now, right now, if I knew what epsilon was supposed to be, it's not that hard to compute an epsilon net. I can just do the following really simple algorithm. I've drawn other sample points here, and here's the algorithm. If I know what epsilon is, I just take any point. Easy. Okay, I take that point, and because I know I need to satisfy the packing condition, I know that I don't take any of the other points inside the epsilon radius circle. I can just throw those points out. Whatever's left is not in that disk, so I can take, again, any point, doesn't matter. I'm not being very precise. I guess I brought my compass. I could have done nice circles. Maybe we'll switch to good circles. Let's do that. Do this right. The algorithm now continues. I just keep taking whatever's any point that's left, doesn't matter. I don't even have to think too much about it. I'll draw these, I'll cover these up in red to make them look good. Once there are no points left, you can check that I indeed have an epsilon net. I was pretty careful about choosing to make sure that I achieved the packing condition. I'm also going to have this covering condition because if there are any points left, then those are uncovered. If there are no points left, it means literally everything else has been covered. So I can just go ahead with that like so. And there we go. So the sample of points I've taken for this given radius epsilon is going to be an epsilon net. I pack and I cover. Great. And in terms of how close the sample is to the original set, the standard metric to be used would be so-called Hausdorff distance, if you've heard of that before. And so I got a sample that's close to my original data set in Hausdorff distance. And if I'm computing anything that's sort of stable up to perturbations of the Hausdorff distance, this sample is going to give me a good approximation to for whatever I'm going to compute. So it's a pretty good start. But actually, I want to be more ambitious than this. I want to say, I don't just want an epsilon net, because I actually don't know maybe what the right epsilon could or should be. Instead, what if I want to compute an epsilon net for every possible epsilon? So no matter what the epsilon is, I'm going to have the epsilon net that's good for that one, for that particular epsilon. And I want to compute them all at once, in one go. It seems maybe even surprising that this is possible. But you can do it, and the answer, which I have already kind of spilled the beans, the answer is going to be this idea of what's called a greedy permutation. So let me show you what that is. The key insight is that if I have a really big epsilon, let's draw 1 point. If I have a really big radius, 1 point would be enough. It just covers everybody. Okay, for a really big epsilon. And for a really small epsilon, if it's smaller than the distance between the closest pair of points, then actually I would have to include all of the points in my net. And so I'm going from 1 point to all the points at some scale. And so what I can do is ask, well, how does it change from 1 point to all of the points? Like as the radius decreases, there's some radius. If I shrink this down, I can't tell which is the farthest. I'm going to plant one that's the farthest. If I shrink this down to this radius, that's a beautiful circle, isn't it? And it needs work, but you see that there was 1 point. I'll make it nice and dark so you can see it. There was 1 point that's just barely covered. If I go any smaller than this point won't be covered. So what I'll do is that will be the next point I add. So this will be the first point. This will be the second point. And now, for smaller radii, let's go a little bit smaller. Now I have 2 points. And so let's pick some smaller radius like this. And you'll notice that at this smaller radius, I have a nice coverage. I'm still covering. And so this is the greedy permutation. There's one point here that if I go any smaller, it will not be covered. Well, that's the next point I'll add. So it's greedy in the sense that every point that I add is the next farthest point from my current set. It's a max-min distance. So the maximum of the minimum distance to any point not in my set is the point that I add next. So add farthest point next. And that's why this is sometimes called the farthest point traversal. It's also called the Gonzalez ordering because it was used in a early paper by Gonzalez, but also it goes by several other names. So the idea, again, you just keep adding the farthest point from the current set, and that gives you an ordering. And the amazing fact is, if I want a particular epsilon now, I just take a prefix of the ordering. That means I take the first k points for some k, and that will give me an epsilon net for some epsilon. And if the epsilon is too small, I take k plus 1 or k plus 2 points, and just keep going in that way. Now, one immediate use for this, in fact, one of the original uses for this was in a problem called Kcenter Clustering. And that's a problem where I would like to put points into clusters. I'd like to identify clusters in data. And in this case, let's say I have nice clear clusters, and I want 3 points, or 3 clusters, and I identify the clusters by their centers. The natural thing to do would be to pick 1 point for each cluster, hopefully, and let all the other points be in the cluster associated with their nearest center. Now, in this toy example, this greedy permutation does a pretty good job because 1 point will be in the first cluster, and then I'll necessarily get a point in the second cluster and a third one in the third cluster. So I'll get a good clustering. And if I look at the coverage radius, that is how tight these clusters are, you might immediately notice that probably I could have done a little bit better if I had chosen a more central point for each of these clusters. In fact, I could have shrunk the radius by about a factor of 2. So the coverage radius is off by about a factor of 2. A kind of amazing fact is that if you take the greedy permutation and you just take the first k points of the greedy permutation, your minimum coverage radius for those k points is always within a factor of 2 of the optimal coverage radius for k points. It's a really cool fact. I won't go through the proof here. It's not too difficult. In fact, if you puzzle over it a little bit, I think some of you could probably even figure it out for yourselves. So that's the kind of most popular use of greedy permutations, is just to do Kcenter clustering. And again, it's an approximation. You can't do better than a 2 approximate Kcenter, at least worst case, unless p equals np. So in some ways, it gives you the best, theoretically best Kcenter clustering algorithm, and it does it for all possible k, all in one go. Pretty amazing. I'll show you another problem that is very similar to the greedy permutation, and it's one where I spent a lot of time as a PhD student. In fact, a big part of my thesis was on a problem of Voronoi refinement. And in a way, this is the same problem, except that I don't have a finite set of points. Let's say I have the entire plane, or maybe I won't go the whole plane. Let's just take this region of the plane. I have this box, and suppose I've taken 4 points so far. Okay. And if I can add any point in this box, and I again take the greedy permutation, I'm going to add, I think it's going to be this point right here is the maximum. Now, if you're wondering what these lines are, this is called a Voronoi diagram, and it really just breaks up the space according to who your nearest neighbor is. In the same way, when we assign points to clusters in the finite case, we assign them to their nearest point. Now I'm assigning all the points in the plane to their nearest cluster center, and along these lines, which are parts of the perpendicular bisector, they actually have 2 different nearest points. We're okay with that. And so the farthest point happens to be right where these meet. And in the problem of Voronoi refinement, you repeatedly add in those farthest points And I'm going to just draw this in. This is an advanced skill to be able to draw these things by hand, so you're allowed to be suitably impressed. And this will be the new Voronoi cell. This blue part will all go away, and I'll have a new cell in this arrangement. And Voronoi refinement is used a lot as a pre-process to prepare what's called a mesh for doing physical simulations, all kinds of physical simulations, especially volumetric simulations, and for solving partial differential equations, heat flow, etc. I was looking at geometric algorithms for computing efficient Voronoi refinements, and here what you do is you refine the Voronoi diagram until you reach some conditions on the what we call the quality of the mesh. And my PhD thesis included what was really the first asymptotically optimal running time algorithms for doing Voronoi refinement in high dimensions. So in a way, again, this is the same kind of problem where you repeatedly find the farthest point from the given points and you add it and you keep going. So going back to even the finite case, you might ask, how do you compute a greedy permutation efficiently? If you took the definition directly, I think you come out with something cubic. That's terrible. If you're just a tiny bit more clever about which distance computations you compute, you end up with a quadratic time algorithm, and that's the one that's used often in practice. But if you know something about the dimension of the data, if it's low dimensional, you can actually do even better by taking intuition from Voronoi diagrams and get something closer to n log n. And there actually is even an algorithm which is basically n log n for a very close approximation to the greedy permutation. So there are these algorithms that take ideas from geometry and improve the running time of the computation of these greedy permutations. So if you like puzzle problems, see if you can first figure out a quadratic time algorithm. And if you're interested in how to do it even faster, I have some code on my GitHub page. You can look up Don Sheehy GitHub. You can see a Python library which implements a couple different algorithms for computing greedy permutations. All right, so that's the classic good idea, greedy permutations, and they show up in data analysis, clustering, etc. Now let me just tell you, I'm going to give you a whirlwind list of some kinds of questions and problems that I'm working on or have worked on recently or hope to work on soon regarding greedy permutations. So one thing we did recently was something I called one-hop greedy permutations. Because even though I said this was a theoretically optimal algorithm, like it's the best we know, we think we can do even as far as approximation ratios go, if p doesn't equal np, that doesn't leave out the possibility that there are heuristics that work much better in practice. And for Kcenter clustering, there is this heuristic which balances between being the farthest point and also being a point that covers the most points. And so recently we showed how to take that heuristic for Kcenter clustering, which really depended on a particular fixed value of k, and show how you can get this greedy permutation version of it that works for all k. So that was a kind of a fun little problem. Another very closely related question is, suppose I want to sample so that it's not just my coverage radius is good, but I want to look at the distance to k different points. And this is used a lot in machine learning where they do k nearest neighbor methods for, say, classification. You want to find your k nearest neighbors and balance between them. So what if you wanted a clustering that is a set of points, or really you should think of it as a subsample, so that if you find 2 points in your subsample, that's almost as good or very similar to, or some guaranteed approximation to the nearest k points in the original sample. We call this KNN sampling. And we showed that actually this standard greedy algorithm, maybe the non-standard greedy permutation algorithm, the slightly better one that gets you like something like n log n time for its computation, can give you this KNN sampling as well if you're a little bit more clever about it. Also, it turns out that just using the greedy permutation of the finite set is really the key to getting asymptotically optimal running times for Voronoi refinement, even in higher dimensions. And lately, I'm interested in a lot of problems also in topology. And for instance, there's a nice question about trying to find the shape of data. So if you have a set and you want to get some qualitative description of its shape, something about the number and arrangement of holes of different dimensions, well, that's really a topological question. And one of the standard techniques in computational topology is something called persistent homology. And again, it turns out that by working with a greedy sample, a greedy permutation allows you to dramatically increase the efficiency of persistent homology computation. Like it takes you from a complex, which was like 2 to the n, down to something linear in size. And anytime you can go from 2 to the n to linear, you really know you're winning. That's the field of what's called sparse filtrations. And currently, I'm also looking at how the greedy permutation itself gives you a kind of data structure in the following way. Every time you add a point, all the points that are not added yet have some nearest neighbor. And so if you look at that arrangement, that clustering, as you add points, every point when it's added, it had a previous nearest neighbor. You think of that as a parent, it gives you a tree. And you can actually do all your standard proximity search queries, that is any kind of nearest neighbor search, kth nearest neighbor search, range search. You can do that directly on this tree, and it turns out to be really efficient both in time and space. So looking at those kind of data structures, and also some questions that I really love, still open questions about, let's say, a simple implementable n log n time algorithm for finding greedy permutations, still open. Nice, beautiful question. Should exist. We don't know if there's a lower bound. It's open whether or not you could ever do better than n log n. That's an open question. How to maintain a greedy permutation dynamically, that is, as points are inserted and deleted. How to maintain an approximate one while points are inserted and deleted. Some things are known here, but not as much as you might hope for. Or you might even ask for a heap-like data structure where points get thrown in, and when points come out, they always come out in a greedy ordering. I call this a greedy heap or a novelty queue. And so these are still open questions that I think are worth exploring. And they all revolve around this simple, great idea of greedy permutations, which, as I said, has been invented and reinvented again and again for at least 40-something years now. So anyway, thanks for staying with the video this long, and hope you have a great day.